And to understand the strategic pivot to methane, one must look past the launch pads of South Texas and toward the horizon of the fourth planet. In the traditional paradigm of space exploration, every gram of propellant required for a return journey must be hauled up through Earth's deep gravity well, accelerated to orbital velocity, and then ferried across the interplanetary void. This is the logistical equivalent of a transcontinental pioneer, attempting to carry every drop of water and every log of firewood they might need for a decade-long expedition before they even leave their front porch. It is a self-defeating strategy. The tyranny of the rocket equation dictates that for every kilogram of fuel you want to land on Mars for the trip home, you must spend dozens of kilograms of fuel just to get it there. And SpaceX's solution is a fundamental shift in philosophy, in situ resource utilization. Instead of hauling the planks for the return cabin from Earth, the Starship system is designed to harvest the trees found on the Martian surface. The Martian atmosphere is roughly 95% carbon dioxide, and the regolith is rich in water ice. By selecting methane as the primary fuel for the Raptor 3, SpaceX didn't just choose a clean-burning propellant. They chose a fuel that can be manufactured on-site using a chemical reaction discovered in the late 19th century. In the Sabatier reaction, a chemical factory in a box. The centerpiece of this Martian refueling strategy is the Sabatier process, named after the French chemist Paul Sabatier. At its core, the reaction is a model of chemical elegance, functioning like a predictable input-output function in a well-defined software module. The code for the reaction is straightforward. NCO2 plus 4H2 leads to CH4 plus 2H2O. In this function, one molecule of carbon dioxide reacts with 4 molecules of hydrogen in the presence of a catalyst, typically nickel or ruthenium, at elevated temperatures and pressures. The output is a clean stream of methane and water vapor. For a systems architect, this is the ultimate stateless operation. You provide the raw ingredients, apply the necessary thermal energy and catalytic surface, and the physics of the universe return the desired product with high fidelity. And on Mars, the implementation of this function requires a multi-step industrial stack. First, solar or nuclear arrays provide the electrical power necessary to perform electrolysis on harvested Martian water ice. This splits the H2O into oxygen and hydrogen. The oxygen is cryogenically cooled and stored as the oxidizer for the Raptor engines. The hydrogen is then fed into the Sabatier reactor, along with CO2 scrubbed directly from the Martian air. The resulting methane is liquefied and stored, while the byproduct water is recycled back into the electrolysis unit to produce more hydrogen. And this closed-loop or circular chemistry is what makes the Starship architecture viable. It transforms Mars from a desolate destination into a gas station. Without the Sabatier process, a manned Mars mission would require a fleet of tanker ships so vast it would bankrupt even a superpower. With it, the Raptor 3 becomes the first engine in history designed to run on fuel produced on a foreign world. And breaking the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky, is the relentless master of aerospace engineering. It states that the change in velocity, or delta V, of a spacecraft is a function of the engine's exhaust velocity and the natural logarithm of the ratio of the ship's initial mass to its final mass. Because of that logarithmic relationship, increasing the mass of the payload or return fuel requires an exponential increase in the starting mass of the rocket. And if a Starship were required to carry its own return propellant to the Martian surface, the wet mass at launch from Earth would be astronomical. The vehicle would be so heavy that the heat shield required to survive Martian atmospheric entry would be prohibitively thick, and the landing legs would need to be massive structural pillars. By utilizing the Sabatier process, SpaceX effectively decouples the outbound journey from the return journey. And this decoupling is a massive optimization in the system architecture. It allows the Starship to be a high-gain vehicle, one that can carry massive amounts of useful cargo, such as habitats, rovers, life support, and people, because it isn't bogged down by the dead weight of return fuel. In the language of computer science, this is a form of lazy evaluation. We don't compute or carry the return fuel until the moment it is actually needed on the surface of Mars. This architectural efficiency is the only reason a 100-ton payload to Mars is even theoretically possible with current chemical propulsion. In catalysis and the Martian environment, while the Sabatier reaction is simple on paper, implementing it in the harsh Martian environment is a formidable engineering challenge. The reaction is exothermic, meaning it releases heat as it progresses. In a terrestrial laboratory, managing this heat is trivial. On Mars, where the atmosphere is thin and thermal management is a constant struggle, that heat must be carefully captured and diverted, perhaps to help prevent the ship's electronics from freezing during the Martian night, or to aid in the sublimation of water ice. And the choice of catalyst is another area where the Raptor's fuel choice shines. Nickel catalysts are abundant and relatively inexpensive, making them ideal for the large-scale industrialization required to fuel a fleet of starships. The reaction also happens to be highly selective. Unlike the complex refining required to create RP1 kerosene, which involves cracking, distillation, and the removal of sulfur and aromatics, the Sabatier process produces methane that is inherently pure. There are no heavy hydrocarbons or branched chains to gum up the works. The fuel produced on Mars will be, in many ways, superior to the methane sourced from natural gas on Earth, which often contains traces of ethane, propane, and nitrogen. And this purity feeds back into the engine's reliability. A Raptor 3 landing on the Martian surface after a 6-month transit will be fed a diet of high purity, locally synthesized methane. Because the engine was designed for this exact molecular signature, the risk of unforeseen side effects in the combustion chamber is minimized. The engine doesn't care if its fuel came from a Permian Basin wellhead or a Martian CO2 scrubber. As long as the input is CH4, the output is thrust. In the logistics of water harvesting, the bottleneck in the Martian Sabatier process is not the carbon dioxide. There is an ocean of it in the air, but the water. To produce a ton of methane, you need a significant amount of hydrogen, which means you need to mine and melt a significant amount of ice. And SpaceX's mission profile assumes the landing of starships near regions with accessible subsurface glaciers, such as Arcadia Planitia. The initial missions will likely focus on prospecting, using automated drills to verify the purity and depth of the ice. Once a source is secured, the Sabatier factory, which may be integrated into the Starship itself or deployed as a separate module, begins the slow, steady work of filling the tanks. And this is where the Raptor as an industrial tool concept becomes most apparent. In traditional rocketry, an engine is a high-strung, delicate machine used for a few minutes of glory. In the SpaceX model, the engine is one component of a long-term infrastructure project. The fuel it burns is the end product of an entire Martian utility grid: power, mining, electrolysis, and chemical synthesis. The Raptor 3 is the client of this Martian server infrastructure. And the Martian engine philosophy. If you were building an engine solely for Earth-to-orbit operations, you might still choose methane for its cleanliness, but you would be less concerned about its specific molecular origin. You might even consider liquid hydrogen for its higher specific impulse or efficiency. However, hydrogen is the diva of propellants. It is incredibly difficult to store. It leaks through the smallest microscopic gaps, and it causes hydrogen embrittlement in metals. More importantly, while you can find hydrogen on Mars in water, it is far more difficult to store for the long durations required for a Mars mission. And methane is the Goldilocks fuel because it balances performance with storable cryogenic temperatures. It shares a temperature range with liquid oxygen, as discussed previously, which simplifies the plumbing. But its primary virtue remains its Martian compatibility. When Elon Musk and the SpaceX engineering team sat down to design the Raptor, they were not just looking at the next 5 years of Falcon 9 replacements. They were looking at the next 50 years of Martian civilization. And by committing to the Sabatier process, SpaceX accepted the challenge of building a more complex engine, the full-flow staged combustion cycle, to make up for methane's slightly lower energy density compared to hydrogen. It was a trade-off: accept higher mechanical complexity in the engine, the Raptor, to achieve lower logistical complexity in the mission, the Sabatier refueling. And synergy of scale. The scale of the Starship and Raptor system is also a function of this refueling requirement. To make the Sabatier process worth the investment in power and hardware, the vehicle needs to be large. There is a minimum viable scale for a Martian chemical plant. By building a massive rocket like Starship, SpaceX ensures that the overhead of the Sabatier hardware becomes a smaller percentage of the total mission mass. And furthermore, the Raptor 3 extreme thrust-to-weight ratio and its ability to be deeply throttled are essential for the return leg of the journey. Burning locally produced fuel, the engine must lift the Starship off the Martian surface, which has only 38% of Earth's gravity, and put it on a trajectory back to Earth. The cleanliness of the propellant ensures that even after sitting on a dusty Martian plane for 2 years while the fuel was being synthesized, the engine's internal valves, injectors, and cooling channels will not be seized by residue or corrosion. And in this light, the Raptor 3 is not just a piece of hardware. It is a manifestation of a Mars-first design language. Every bolt, every weld, and every line of code in its controller is predicated on the assumption that the fuel it consumes will be pulled from the air of another planet. And from chemistry to kinetic energy, we have explored why methane is the chosen medium: its cleanliness, its cryogenic sympathy with oxygen, and its ease of manufacture on the red planet. But knowing why you are using a fuel is only half the battle. The other half is the how. To extract every possible bit of energy from the methane-oxygen bond, the Raptor 3 cannot use a simple, open cycle like the engines of the past. It requires a machine of staggering internal pressure and complexity, a machine that manages the flow of these fluids with the precision of a high-pressure hydraulic system. And the sheer volume of propellant that must be moved through the Raptor's heart to generate 280 tons of thrust is difficult to visualize. It is not a trickle or a stream, it is a thundering torrent. To understand the mechanical violence required to harness the Goldilocks fuel, we must move from the molecular level to the macro level, from the chemistry of the Sabatier plant to the massive pumps that feed the flame. And this transition from chemical potential to kinetic force is best understood through the lens of fluid dynamics. To appreciate the full flow revolution of the Raptor 3, we must first grasp the sheer scale of the plumbing problem. And 3.1, the water hose analogy, moving mountains of liquid.